Okay, so we found the wave function of our system, just n e to the ikx. And when we applied the Hamiltonian operator, right, we found that indeed this wave function is a good wave function for this system. We get a solution to the eigenvalue problem, and then the constant that multiplies our wave function is indeed the energy. So it's just k h bar, that quantity squared over 2m, is equal to the total energy, the kinetic energy of our particle here. The important thing about the wave function is that it is a complete description of the system. So if we want to measure another property of the system or know what it is, all we have to do is find the operator that corresponds to that property, apply it to our wave function, and when we find the eigenvalue, that will correspond to the property described by that operator. So let's say we want to know the linear momentum. Again, we have an operator that corresponds to linear momentum. That operator, p hat, is going to be h bar over I times the derivative with respect to x, our one coordinate in this system. And then all we have to do is apply p hat to the wave function, and we'll get the value of p, the eigenvalue of that operator will be the linear momentum. We know psi, so we can substitute that into here. H bar over I times the derivative of psi with respect to x, right? That's just going to be h bar over I n I k e to the I k x. Multiplying through, we find that we get, when we operate with the linear momentum operator on psi, what we end up getting is h bar k n e to the I k x again. That's the initial wave function. And so we end up with k h bar times the initial wave function, and this must be the value of the linear momentum. So now we have a value for the linear momentum, we have a value for the kinetic energy, and indeed classically we would have said, oh yeah, the kinetic energy is equal to p squared over 2m. And indeed, that's exactly the result we have here, which is just equal to kh bar, the quantity, squared over 2m. So we've used the methods of quantum mechanics, and again, we got the classical result. The linear momentum can be continuous, the energy can be continuous, the relationship between linear momentum and kinetic energy is the same. And indeed, if we plotted kinetic energy versus the wave vector, we would find a nice parabolic relationship where if k is positive, we're moving to the right, and k is negative, we're moving to the left. And there's this nice quadratic relationship between the energy and the wave vector k. Okay, we found the wave function of the system. We applied the Hamiltonian operator and obtained the energy, allowed energies, continuous energy distribution for this unconfined particle. We applied the linear momentum operator. The wave function was also an eigenfunction of the linear momentum operator, and so we found the value of the linear momentum, again a continuous variable. We've applied the quantum mechanical treatment, but we get the classical answer, and we get the classical relationship between linear momentum and energy. Now what's this wave vector, and what else could we get from looking at a classical solution? So what if we looked at the time-dependent wave function of a plane wave? In that case, what we'd have is the time-dependent wave function depends on both x and t, right, would be equal to, some normalization constant e to the I times the quantity k minus omega t. Omega is an angular frequency, k being our wave vector, right? Now, classically, k, this wave vector, its absolute value actually, would be equal to 2 pi over lambda, the wavelength of our wave. But here we've also derived another expression for k, that k is related to the linear momentum, and therefore equal to, just solving from here, right, k is equal to p over h bar. Now we can solve that for lambda. Lambda equals h over p. And indeed, we have found the de Broglie relationship. The de Broglie formula for the wavelength of a particle as related to its linear momentum. So this quantum formula was hiding in the mathematics of classical mechanics all the time. That's good, because classical results should be one limit of the quantum mechanical results. But here, there's no reason in classical mechanics for big particles to ever find this. Why? Because for large particles, wavelength is not an important factor. Two, there's no reason to find the Planck constant unless you're looking at small systems. Small, when are they small? Small when we confine a particle with a potential, and at least one dimension of our confinement becomes comparable in size to the de Broglie wavelength. Then a quantum mechanical treatment is necessary, and we'll find quantized energy levels instead of continuous energy levels. We get continuous energy levels when a system is not confined, or if the confinement is so large that it's not comparable to the size of the de Broglie wavelength.